Good afternoon, or good morning, or good evening to everyone, and welcome to this CMCC webinar entitled Climate Reanalysis at the Local Level, How to Support Sectoral Application in Italy. I am Monia Santini from the Euro-Mediterranean Center on Climate Change. And this webinar will illustrate in particular two methods, statistical and dynamical, to improve the detail of the last generation climate reanalysis era 5. So to support local application for different sectors and for different users. This work is conducted in the framework of HIGHLANDER project, funded by the Connecting Europe Facility CEF Telecom program of the European Commission, and the project is coordinated by CINECA, the Italian Inter-University Consortium. The webinar will be held by Estibaliz Gascon from ECMWF, the European Center for Medium Range Weather Forecast, and by Mario Raffa from CMCC. Esti has been working as a scientist in ECMWF since 2016. She has experience in product for high impact weather and on ECMWF integrated forecasting system, in the post-processing in particular, and the statistical downscaling methods, especially for precipitation. Mario is a CMCC researcher since 2015. And is working on climate simulation with experience, especially in the regional model Cosmos CLM at very high spatial resolution and coupled with the urban schemes. Before to start, let me provide a few information about CMCC. Let me change the slide. Okay, CMCC is a Italian foundation composed by different research center and university in Italy, and the mission of CMCC is to investigate and model the climate system, but not only referring to the atmosphere or ocean dynamics, but also to study the possible impact of climate change up to support mitigation and adaptation policies. CMCC Foundation is composed by different institutional partners like Italian university and research centers, and is organized as a network of offices distributed in Italy with offices in Lecce, Caserta, Viterbo, Sassari, Bologna, Venezia, and Milano. And these offices host different research divisions that conduct a CMCC interdisciplinary research, because CMCC conduct research not only related to climate modeling, but also to impact modeling up to the evaluation of impact on the socioeconomic system. Another peculiarity of CMCC Foundation is the supercomputing center that was renewed this year, that allow to produce a lot of prediction and projection on the climate that in turn can feed impact evaluation. We conduct CMCC, we conduct research, but we also contribute in communicating and disseminating this research, the results of our studies, and also we support education through supervising PhD thesis, master thesis, and also by participating in the conduction of summer, winter school, and so on. Other tools for disseminating our research are, of course, publication, but also events like this webinar. And after the webinar, you will be allowed to answer some things to the speaker, and you can use the chat in the Zoom tool. And I just ask you to today we have two speakers. I just ask you to indicate if the question is for one of the speakers or for both the speakers. And final remarks about this webinar. This webinar will be recorded and you will find it in a couple of days on the CMCC YouTube channel. And also I invite you to follow CMCC activities on our social media. The last information is about the next webinar that will be held next week on June 22. And will concern strategies for resilient infrastructure, a climate risk assessment framework for airports. Now I give the floor to Esti in order to start her presentation. I will stop the share of my screen. Please, Esti, you can start.
Thank you very much, Monia, for presenting. I will share my screen and see. Okay. And now, okay, yes. Can you see? Okay. Yes. Good afternoon, everyone. So thank you, Monia, for introducing us. Well, I'm Estibaliz Gascon. I work in ECMWF, and in the Highlander project, I focus mainly on the application of a post-processing of in Era 5. This post-processing is some technique that has been already tested in the ensemble forecast in ECMWF, and it's called easy point. So let's see what is this easy point post-processing. Well, here I just put an example to see and understand easily why we decided to do this post-processing. Imagine that you have this map of the north of Italy and you extract just a pixel in Era 5. And in Era 5, the pixels has a 31 kilometer resolution. So we can see that it includes different cities, villages, areas with different characteristics. So the main purpose of the easy point post-processing is to anticipate the weather variations inside of these grid boxes. And in this case, it can be for the forecast of the reanalysis and provides some input or some idea of what is happening inside of the grid box, not with the mean value or the average value that we provide now. So this the next explanation I will give is focused mainly on precipitation, but in this investigation and this post-processing, we apply also for temperature. And also it's focused on the forecast, but as we apply this methodology in the Era 5 forecast, not exactly in the analysis, it will be useful for both. So what is easy point? First is an ECMWF post-processing system that tries to improve probabilistic forecast or other type of forecast of the surface weather, which includes rainfall or temperature in this case. So if we concentrate on rainfall, what we want to say with the accurate rainfall forecast? Well, accurate, we refer that the forecast of extreme point rainfall is in the right location or in the right lead time in this case. So to do that, we should anticipate different degrees of subgrid variability and account for the model biases. So we should understand what is happening inside of the grid box and also the general model bias. So to understand it better, we have these two examples of rainfall totals. Imagine that is a specific time. And we see the accumulations of precipitation for one case, large scale system, and another case with convective system mainly. So we can see that, imagine this grid box is your pixel in Era 5. So we can see that the values in the first case is between 1 and 4 millimeters inside of the grid box, but the mean value is 2 millimeters. So not many differences. So we don't have too much subgrid variability, but still there is something. And on the other case, we have values inside of the grid box between 0 and 80 millimeters, but the mean of the model grid box may be 6 millimeters. So we are not really picking these extreme values that probably are interesting if we are evaluating more extreme weather. So here we can see that we have lots of subgrid variability. So what is this global? Because in reality, we are producing global values, even if we will crop later for Italy. So what is this point-based rainfall forecast? So it's a new statistical post-processing system that references relevant physical processes in rainfall generation mechanisms, but this mechanisms are not well represented in the raw model output because of this mean grid box. And this allows to us to anticipate the subgrid variability and correct also the biases in the model. So we can apply this to everywhere in the world, and I will explain later why we can apply everywhere. And we correct, as I say, the two main points, the dependent biases in the weather-dependent biases in the model or the reanalysis, and the weather-dependent subgrid variability. And in different situations, one of these two aspects can dominate. So the concept to do this post-processing is the concept of remote calibration. What is this? So let's see this example. Imagine that we want to forecast rainfall for Louisiana, and the conditions are mainly convection, light winds in summer, and we are in a flat area. So the question is, how did the model perform a short range in other sites with similar conditions? So if we pick the place, we can see that in many different areas around the world, we can see the same conditions, or we found the same conditions. And we are going to extrapolate or consider that this error at those remote sites provide a good guide to assess the model reliability for those particular conditions somewhere else. It means that the model will have similar errors everywhere in the world with same condition or same weather conditions. This is the first assumption of this post-processing. So this is a real example of remote calibration. Imagine that you have extreme weather in the UK, and it's mainly convective precipitation, light winds with medium values of total precipitation. So we try to pick how many times we have, or how many observations we have of those conditions in the UK in 1 year, and we observe only 30 cases. With 30 cases, you cannot extract an idea of these biases and subgrid variability. However, if we take into account all the observations around the world with similar conditions, we obtain almost 30,000, which is good enough to consider and to have an average of the biases for that weather type and that specific place. So you can see that we have several cases around the world. So what is the main advantage of this remote calibration? First, that it provides immediate and massive training data set, because we use global data set, from a much shorter training period. We only need 1 year of training to obtain thousands and even millions of observations to take into account in your division of weather types. We don't have non-stationary issues because we can calibrate any point around the world if we have observations with similar weather types around the world. And also it can facilitate point-based rainfall forecast for any lead time for any grid box. In this case, it's ERA 5, so we will have only for the first day of the forecast. So how we establish the different weather types? Well, the main tool to divide and to discuss that and to decide the different weather types is the mapping functions. Here you have a mapping function, so it's this plot with relative frequencies of forecast error ratio. We define the forecast error ratio like the observation in a specific point minus the forecast, so it's the mean grid box forecast, at that point divided by the forecast, so it's a simple equation. So each weather type or each specific condition that we calibrate separately in this easy point is defined by one of these mapping functions. So what we can say is that in this mapping function, what we can see is the relative frequency of this forecast error ratio. In green, we can see the areas or the forecast error ratios that correspond when the observations are drier than the forecast. So the model or the reanalysis overestimates the precipitation. On the other side, in yellow and especially in red, we have observations wetter than the forecast. So the model or the ERA 5 underestimates the precipitation. And in white, you can see the bar that we consider that more or less is the observations and the forecasts are in good agreement. Okay, so then we have different predictors to classify in these weather types. And this is an example of part of a decision tree. So on the top, you see the mapping function with all the weather types. Then we divide in different types of precipitation, mainly convective on the right, mainly large scale on the left. You can see that the shape of the mapping functions are different. Later, we continue with the amount of total precipitation. Later, we have another predictors, which are the wind speed, and so on. So this is just an example of how we develop this kind of weather types, how we define them based on these mapping functions. But probably you say, okay, how we really define these predictors and how we classify them. Later, I will show just one example or some examples to discuss that part. Okay, so what we do in Highlander and what we did in CMWF in Highlander to apply this post-processing? Well, in the past, as I told you, we apply this post-processing in forecast, but in this case, we want to apply in ERA 5 reanalysis and also in the subseasonal forecast. But I will only focus on the first part in the ERA 5 reanalysis. So in this case, the EC point is defined by 99 percentiles, so we will provide probabilistic reanalysis instead of deterministic. And also we have some bias corrected grid box values that they are experimental products. So I won't show too much of that. We will apply this technique for rainfall, for 12-hourly accumulations and 24-hourly, and for 2-meter temperature for daily maximum, minimum, and mean. We produce this database globally for 70 years of data. We apply, as I said, for the ERA 5 forecast, not the analysis, pure analysis, because we have these variables, accumulated variables only in the forecast. And we have global fields, but only Italy will be available in the Highlander platform. However, just to mention that if everything, well, after testing these products, is probably that we add in the future, or we can add in the future the global fields in the climate data store if everything goes well. So finally, just to say that this will be like the first probabilistic reanalysis with better representation of the extremes. So this is the intention of creating this better representation of the extremes in reanalysis. So here is how, because probably you are asking how we convert these mapping functions in the correction, no? So you have here this one mapping function from a specific weather type. And we have one field of reanalysis with a specific grid box for a specific date and a specific variable. So what we do is to see for each grid box, what is the mapping function, and create 100 new ensembles, so 100 new outputs of the ERA 5 reanalysis, correcting the raw reanalysis proportionally with this forecast error ratio. So we will create the corresponding corrections of all the database that we have, but we extract just 100 to have a sample because we cannot correct with all the observations in all the cases that we did. As you remember before, it was 30,000 for one specific case. So we just summarize in 100, and this 100 will be proportionally corrected in the reanalysis. So here is just an example of what we decided for to create the predictors. So on the left-hand side, you have the predictor that we already created in an operational product, and we decided for the AC point rainfall 12-hourly for the medium range forecast. So this operational product has been online and operative since 2019. And you can see the different variables that we decided to include as predictors in the decision tree. On the right-hand side, you can see the predictors that we have selected for similar products, so for 24-hour rainfall and 12-hour rainfall in ERA 5. And we investigated how to include new variables, so just to improve even more this easy point post-processing. So as you can see, the blue, the variables selected in blue, like convective precipitation ratio, total precipitation, wind speed, CAPE, or solar radiation, are in common with the ones that we already have in our forecast. However, we also included here the land sea mask, the standard deviation of the filter sub with the orography, which gives an idea of how good is the representation of the orography in the grid box, and also the maximum 2-meter relative humidity. So I'm not going to go in detail, just to explain what we selected as predictors. So here is an example of one of if you see here is on the top, the first predictor is the convective precipitation ratio. First, explain that these predictors were selected based on meteorological knowledge, on well-known issues that we already know in ERA 5 for specific variables, and also we apply some statistical analysis based on the Kolmogorov-Esmirnov test, and we decide the breakpoints based on that. So it's a mix between meteorological knowledge and statistics. So as I say, this is the influence of the convective precipitation ratio in the 24 hours precipitation biases. And on the bottom, you can see the cases when we have mainly large scale precipitation, so stratiform precipitation, in the middle mixed precipitation, and on the right, the mainly convective precipitation. You can see that they are very different between them, the plots. And we can extract some conclusions. First of all, the convective precipitation has larger overestimation, but also higher underestimation. You can see that the extremes are higher in both sides. Also, you have the large scale precipitation, which is better, the forecast, let's say, is better than the convective precipitation, because if we focus on the white bar in the middle, we see that the spread of the errors are lower, and the white bar is also taller. But we can see something interesting. The bias correction per grid box is the same for mainly convective and mainly large scale precipitation, 0.94. This is why we give importance to this easy point calibration, considering all the possible ranges of biases that we have, because having totally different representation of the errors in the mapping functions, the bias correction can be the same. So this wouldn't be the best or the most accurate way to correct in many cases when we have a big subgrid variability. And the easy point in considering all the errors distribution would be more accurate. So here is another example for the predictor selected for the 2-meter minimum temperature. And in this case, the predictors have been classified in 4 different aspects. So first of all, we consider the orography with the Lancy mask and the standard deviation of the filter subgrid orography, which I say that is how well is represented the orography in the ERA 5 grid box. We also have the urban fraction. Later, we classify in different 2-meter minimum temperature ranges. We also consider 2 different surface variables like snow depth and leaf area index, which can affect quite a lot to the 2-meter minimum temperature. And finally, we consider aspects of the stability, which is important depending also on the surface that we have. If we have snow, we have more vegetation and so on. So we also consider this. In total, we have 9 predictors for this decision tree. Here you have schematically how we divided the first 2 predictors, so the Lancy mask and later the standard deviation of the orography. Let's have a look of the representation of the mapping function with these 2 predictors. First of all, this is the Lancy mask, and we can see that in this case we have just the forecast error as represented in the mapping functions, which corresponds to the observation minus the forecast. In this case, we have classified into different branches. So we divided these weather types in 2. First is the Lancy mask witness lower than 0.5. In these cases, it includes areas where there is land, but the whole grid box is considered C, because it's how it's defined the Lancy mask. So lower than 0.5 is considered like C. In this case, we see that we have higher errors or larger errors. So the model is too warm regarding to the observations on that specific branch, and the general bias is higher as well, the grid box bias, compared to the Lancy mask greater than 0.5, where in reality, we have land and we consider that the grid box is land. So the exchange of energy and moisture between the ocean and land and the land, the atmosphere and the land is correct. So here is one example of how different can be the mapping functions with this predictor, and here is for the orography. So how we define or how the errors can be different also in the 2-meter minimum temperature if we are in the mountains or flat areas. So on the left, you can see flat areas. We see that the model tends to be too warm, but we also have some tendency to be too cold in some aspects, but mainly too warm compared with the observations. And then in the mountains, you can see that the spread of the errors is much higher. So the errors are higher in general, and the model tends to be too cold. So it overestimates the minimum temperature. So it's too cold if we compare with the observations. So here the conclusion is the overnight 2-meter temperatures in the ERA 5 forecast tend to be too cold, but especially over rough mountainous areas. And here is just an example of one event. In this case, is the storm Alex that affected northwest of Italy between the 2 and 3rd of October 2020. And we are going to use these products to see how it worked. So here you can see the most affected area for these flash floods. Some accumulations on 24 hours in some areas were even 600 millimeters. So the effects of the flooding were devastating. If we do zoom in this area that we have this box, we can see first that the era 5 row for that specific day corresponds to the left-hand side on the top, and we compare with the observations. In general, the areas, the most affected areas were well defined, but we see that in general are also underestimated, the values. If we go to the different percentiles in this era 5 easy point, we can see how this the 95 percentile and the 99 percentile picked much better and extract the maximum values better than the raw era 5 in the most affected areas. Indeed, we can see that only in the era 5 99 percentile, we can identify these gray dots of more than 500 millimeters that we see in the northwest area of Italy. So it's pretty extreme, but the easy point can understand or pick those values. Here, just to reduce the percentiles, we compare the 50 percentile and the 90 percentile, just to show that the most affected areas are still in our distribution of these percentiles as well. And finally, just to see exactly how it works, we converted these percentiles in probabilities, and we can see that the probabilities of total precipitation greater than 100 millimeters, which in the colors on the top, it would be from the pink colors. We see that in the era 5 row, the areas are not well picked. So we have some areas, but they are underestimated, the maximum possible precipitation. And if you see the plots in the probabilities of total precipitation greater than 24 hours, even with low probabilities, we can identify quite well the most affected areas. Even if we go ahead to 300 millimeters, we also can see these areas, which it corresponds to the dark blue and and also the gray areas. So with low probabilities, but the era 5 can identify. So this is just a summary, it's very small example, but we can just say how I wanted to show how the extremes can be really predicted or really identified better with this era 5 easy point product. And well, that's all. I hope that it was not too long. So I pass the turn to the next speaker. Thank you very much.
Thank you, Esti. Now we can proceed with Mario.
Thanks, Esti. Thanks, Monia. I share my screen. I guess you see my screen.
Yes, perfect.
Okay. Now, in this second part of this talk, we focus on the dynamical downscaling. We saw how to turn climate data at global scale into detailed information to support the impact model. So in the Highlander, CMCC developed the dynamical downscaling of the era 5. So we produce a new additional gridded data set over Italy at 2.2 kilometers. So I'll present you the assessment of the experiment, how we set up the new scenario experiment in the future. And in the last phase, I'll show you some application of this data. This new dataset have been produced in the Highlander project, led by Cineca. In this project, Cineca shared this facility and skills to run this computational demanding climate and weather prediction, not only long-term climate simulation, but also, as you will learn from the first part of the webinar, to increase the prediction with the statistical experiment. All these data can be used as input for the downstreaming application preparation service. That means climate service in different sectors, from agriculture to forest fire detection or human well-being. Now, some basic information about how to turn the global climate model into local information. Global climate models are important tools to assess the impact of future greenhouse gas concentration, but often they run at very coarse resolution with degrees that often larger than 50 by 50 kilometers square. So this is too coarse resolution for some application for impact models. So to solve this issue, different downscaling techniques has been adopted. Now we focus on the dynamical downscaling that's based on the nesting a regional climate model at very high resolution into a coarse resolution GCM, or in general analysis or scenario data. This second dynamical downscaling use lower resolution climate model, in most cases CM, as a boundary condition and physical principles to reproduce the local climate. So RCM are computationally very demanding in terms of resources, in terms of storage and other issue. This is a description of this new grid dataset. We performed the dynamical downscaling and provided very high resolution climate data at 2.2 kilometers of spatial resolution and 1 hour for temporal resolution, and covered the period from 1989 to 2020 with the model Cosmos CLM. This run was performed on the cluster Galileo of Cineca and covered all the Italian peninsula that you can see in this map, the computational domain. The model includes some physical schemes, but I want just to highlight that we include also the urban parameterization to take into account the effects of the cities and feedback of atmosphere in some complex orography or urban areas that take into account the urban canopy of the land. The list of variables, the output model meets the user's requirement according to the partner of Highlander and according to the application. We focus, we have fields from temperature to humidity to wind, but also fields related to the soil, on the soil level. Now, I just want to give you some evaluation of the performance of the Cosmos CLM at 2.2 kilometers and with an attention of 2 meter temperature. On the left, you can see the seasonal mean temperature. The first column is the EOBS used as a reference. The second is the ERA5 driven that drives our downscaling, and the last is the very high resolution dataset. This color can be explained through this table on the right when we give information in the sub-areas of the Italy divided into NUTS1 from north to the insular. And you can see how the very high resolution dataset show a warm bias, especially during the summer in terms of bias. Bias means difference model minus observation with a slight underestimation. So we get a slight cold bias during the winter. On the right, you can see the ratio of standard deviation. The ratio of standard deviation gives us information about the variability. So moving from the ERA 5 to the very high resolution dataset, we have more variability due to the refinement of spatial resolution. From 2-meter temperature, we derive some climate useful to characterize the area in terms of climate indices. Climate indices, in this slide, you can see the ice days, the summer days, the frost days in terms of radar graph. The radar graph, you can see in the vertices of this graph, there's the NUTS one. So from north to the insular, you can see the mean value of the ice days, summer days, and so on. You can see how the very high resolution dataset in the red line give us new information that ERA 5 doesn't have, cannot give us as information because it does include some physical processes, it doesn't include some schemes that the model can be reproduced. And generally, the very high resolution tends to improve this information. And now we focus on the total precipitation. If you consider the precipitation in the left, you can see also for this case the mean, the seasonal mean precipitation from the reference to the very high resolution dataset. In this case, in comparison with the observation, ERA 5 tends to increase precipitation across Italy, especially during the summer and the spring. The blue line represent a wet bias up to a wet bias that, this bias is reduced in the very high resolution dataset with some exception, for example, in the South Italy, where we have this marked wet bias. In terms of standard deviation, we have the same information about the variability that in this orography, in this complex chorography of Italy, it's important to take into account this variability due to the complex orography, for example, in the north part of Italy, but also overall the peninsula, due to the mountain region and the coastal area. We computed some indices based on precipitation that are useful. That are useful, for example, for farmers, in the agriculture sector, because we have the consecutive dry days, the consecutive wet days, and from this kind of graph, you can learn how this area. How the area is characterized in terms of precipitation, in terms of dry days. For example, you can see from this graph that the northern part of Italy is the wettest in terms of consecutive wet days. Other are drier than the insular, and south are drier in terms of are drier with respect to the other regions. But the first experiment, so the dynamical downscaling of ERA 5 is known as evaluation experiment because we have the reanalysis that drives the experiment. But this evaluation experiment is mandatory for the projection run, climate projection run, that we are running in this last phase of HIGHLANDER project. So CMCC is running the dynamical downscaling of the GCM to provide a very high resolution climate data, but under the IPCC RCP 8.5 climate future scenario. For this experiment, the setup is different compared with the evaluation experiment because we have to take into account the difference between the coarser resolution of the GCM that drive all the chain and the target resolution of 2.2 kilometers. So in this case, for this experiment, we need an intermediate climate simulation at 8 kilometers that CMCC published some years ago. The domain is the Italian peninsula. In this case, the period ranged from 1989 to 2050. So it includes historical run up to 2005 and the scenario, future scenario under RCP 8.5 up to 2050. Also in this case, the variable list is the same and the frequency is 1 hour for all these variable. For this experiment, Cineca let us the possibility to run this long-term simulation on the new cluster Galileo 100 that completed the pre-production phase. Now, I just want to give you an example how the output of the dynamical downscaling can be used for the decision making, for the impact modelers, for one case use about the soil erosion. Soil erosion affects many sectors because it reduces the soil thickness and fertility, but also causes physical damages to agriculture field, but also means ecosystem, tourism, urban areas as well. And also insurance is interested because direct and indirect economic costs to recover damages. So in this case, this is our chain. We performed the dynamical downscaling of VIRA5 in the reference period and the GCM in the future scenario and provide as input the hourly precipitation. So hourly precipitation is the input for this datos block for the climate service related to the soil erosion that implement the revised universal soil loss equation. I'm not an expert on this topic, but I know that this equation takes into account the unchanging factor related to topography, factor that changing slowly related to the soil properties due to soil tillage and other practices. And this equation embeds the rainfall erosivity as a triggering factor like rainfall erosivity to produce the rainfall erosivity and then the soil loss. So you can see that the output of this chain is a map and statistics about the soil loss in Italy. But if you want to how this data can be accessed, CMCC developed the data delivery system. There's a web users interface based on Python client where you can submit your request about the variables, about the period. You can select a subdomain of Italy, and the delivery system can you can download the NetsDF data or about your request. The output model are free for partners of Highlander project, but the end users can request this data under a specific license of Cineca and CMCC, and you should askly cite the reference about this product. So to conclude, CMCC in the Highlander project provide a new dataset, a gridded dataset of unprecedented high quality and very high resolution historical and climate projection for Italy. The climate projection will be available in the next months. Some highlights about the performance of the model. The very high resolution reanalysis shows good agreement in terms of 2-meter temporal with a slight a warmer bias during summer that could be taken into account for the application. There's a slight overestimation, a wet bias for all the season, more or less overall the Italian peninsula. And analysis of extremes through the climate indices reflect the tendency to amplify the climate dynamics to the spatial refinement resolution. In terms of application, there are many sectors affected by climate change that that this data can be used because there are decision-maker tools for the agriculture sector, for the forest fire detection, for animal and human well-being, that can use the hourly precipitation, the 2-meter temperature, and other fields, atmospheric fields. Also for this kind of data are useful for water management or forest management, and the data delivery system is the tool that can allow to download the NetCDF data to give us as input for the impact model. And that's it. Thanks.
Thank you, Essi and Mario. Now I'm collecting some questions. There was an initial question about the advantages and limitation of the two approaches, statistical, dynamical ones, but I think that one of the slides of Mario already answered to this question. Now, two other questions are coming. The first one is, can you please comment on how the ensemble and the single run approaches differ in climate projection, and in particular in this case, where these very high resolution runs are placed in the uncertainty range of ensemble projection, if none, of course? So if understood, the question asks how these high resolution run are placed in the range of ensemble projection. Have you conducted, Mario in particular, some experiments, some verification on that?
I just want to add some information about the projection, because we know that in the community, in the scientific community, the ensemble is the best way to take into account the uncertainty, but in this case we run the one single run that, but we are are that the uncertainty in the evaluation experiment are in line with the error at this resolution. I don't know if answered the question.
Okay, then we have just another question. Okay, maybe I can clarify this one, because Mario, you said that these downscaled data are free only for Highlander patterns, but I think that we decided at the end a few days ago that they will be open also for other interested people, but just to clarify the final use, and in any case to cite the right to use the right citation and acknowledgement for this data about funding and so on. Another question, if I understand well, ask about the availability of the presentation. I'm not sure to understand if they are asking for the presentation, but the webinar, The webinar was recorded, so it will be available on the YouTube channel, and not the slide, not the presentation, but you can see again all the slide through this through the recorded webinar. Let me check. Okay. Another question is about soil erosion, but soil erosion was just, I can answer because I was involved in that work concerning soil erosion. But in that case, Mario, was just to indicate that these high resolution run were used for the rainfall erosivity factor of the soil erosion model. So concerning other factors related to the farming techniques, of course, we did several scenarios, but it is not related to this high resolution simulation. Then other question. Let me check. Okay, Lavinia Laiti that asked the question about where the simulation are placed with the uncertainty range. Okay, she wants to clarify the previous question, and now she asked, are we on the wetter side of the uncertainty range of available projection ensemble, for example, considering Eurocortex data, or in the drier? And for temperature, are we on the colder or warmer side?
For this experiment, we have the convection permitting resolution. On the Eurocortex, we have 12 kilometers. So in this kind of experiment, we introduce, we have now other ensemble model to compare our data. For example, in the Cortex, we have the flagship pilot studies on convection, and we know that our wet bias, especially for precipitation, is in line with this data. Okay.
Sorry, I'm checking if there are other questions coming. No. I have a question for Esti, if possible. Just to understand, because you mentioned it as a variable used in your approach, precipitation and temperature. I imagine that the use of this approach for other variables could be limited by the number of observations, because of course other variables are not measured like temperature, precipitation, but have you a roadmap, a sort of plan in order to start to use this approach also for other variables, and which ones in particular? I don't know, wind, for example.
Yes, this aspect has been discussed since the beginning of the technique. For now, we don't want to go further than temperature and precipitation. What we could do probably is extend the range of the precipitation, for example, so the accumulated periods. So for example, we are currently producing for the forecast, the ensemble forecast, the 6-hourly easy point precipitation for Italy, indeed. In the Mistral project, we produced that, and it's available now. So we can do it the same for rainfall in Era 5. However, for example, the wind, which it would be a variable to do that, is not the best approach, because the wind has many other components and very local components that are difficult to correct with the weather type. So probably for that, we thought that it's better to apply some machine learning approach and some other type of downscaling in a specific location, probably dynamic downscaling, it would be much better than that. But we don't see this approach in that in the wind, at least. I don't know for other parameters, it could be considered, but for now we are testing this, and probably we will apply, if in Era 5 is fine, we will apply for the ensemble forecast as well, for the temperature.
Okay, thank you very much. Then there is another question related to the availability of data in the repository on the data delivery system. I can say that for the downscaled reanalysis, data are already available, while for the projection, they will be available soon. Another question is maybe for you, Mario, because the question is, have you planned to do other projection under other RCP scenarios beside RCP 8.5?
For the Highlander project, we define only this worst case of scenario.
Okay, and the last question I can see here is from Paula Fajan about projection. Has it been validated about the wind intensity in the historical period? I suppose not yet, because you just finished this
yes.
this simulation. And I have a question for Mario, then I think that we can close, related to the fact that, of course, ERA 5, one of the main advantage of ERA 5 reanalysis is the hourly time step. Is possible to use this dynamical downscaling approach to also not only to downscale in a special term, but also to disaggregate data at sub-hourly level? Have you planned some experiment on that, for example, to have half-hourly data?
We tested some in some small cases studies to have sub-hourly precipitation and other data, but we think that hourly precipitation is a limit of this kind of experiment, only especially for the validation.
Okay, thank you very much. I cannot see other questions, so maybe we can close here, but I want to remind to attendants that it is possible to ask other questions to speakers. And so for attending this webinar, and see you soon. Bye-bye. Ciao.
Thank you very much.
Thank you very much.
Thank you very much. Thanks.